All right. Well, welcome back, guys. Week 2, day 1. Wanted to go over uh, some foundational information and then proceed with the next notebook for Python. So while I'm yapping about data and elementary statistics, if you want to download notebook number 2 into your notebooks directory, I intend to get to that before we are done today. But this is kind of a recap of stats, just from the like I said, the elementary viewpoint. It gets really complicated as you get into advanced statistics, projecting and forecasting and whatnot. But first, I wanted to cover something that you guys turned in for me. Sources and types of data. This won't take too long. For most folks, I think I have a fairly comprehensive list here, but jump in if I leave something out. Most of the data that all y'all are dealing with is in some kind of a functional support system, like a banking system, or in the case of Intellex, an environmental monitoring and reporting software as a service application, HR systems, customer resource management systems, production support, supply chain management systems, enterprise resource management. I'm sorry, enterprise resource planning systems, ERPs. Pretty sure a lot of the data Seth deals with comes out of point of sale. These are all kind of lumped into operational systems or functional support systems. That's where the data comes from. Sometimes you can do reporting in those, and you can do analysis in them, but generally speaking, not. we for the most part have to pull data out. Like I think all of you guys are dealing with pulled data that's been pulled, typically as CSV. That's the universal constant. And we'll talk about that on the next slide. And then some of you are dealing with custom developed databases, which have been implemented with a software developer, and are moving towards or are using a data warehouse, which is your structured central repository. So that's cool. But there's data available for projects and analysis, practice out there, in a bunch of different places too. There's government websites. I filed my taxes recently, and I thought, good grief, Arkansas is taxing you left and right. State income tax. If you don't travel much, it's probably not too much of a shock how high Arkansas sales tax is, but it is really high. And then I got a bill for hundreds and hundreds of dollars for personal property tax for my cars and my motorhome. And I started thinking, good grief, what is going on here? So I went to, this is probably Wikipedia. I found a table of tax dollars spent per capita, per resident, which gets you, apples to apples. And Arkansas was like number 5. We spend a lot of money per person, a lot of public funding per person, more than some of the other states that you might think. But I got that off of a government website. And depending on, what you're doing at work, you may need government work. I don't know if like environmental data. Do you ever go? I apologize. Is it Kevin or Edgar that's works with Intellex? Works at Harvard.
That's me.
Kevin, do you need environmental data from like EPA websites or anything like that, or state level data?
We use like energy subregions, and those I think that's where we get some of our factors from when calculating like emissions.
Yeah, and Entergy, the utility.
Hmm.
Yeah, that's very nearly a government website, regulated natural monopoly. So yeah, Bureau of Labor Statistics, virtually all government agencies have some sort of an information portal, and then there's data.gov that is like a central website into those different repositories. Um, and depending on what you're doing in your jobs or your future studies, those can come in handy. Commercial providers, you can spend money for data all day long. It gets packaged, repackaged, enhanced, and sold. Goodness, a lot of the graduates of the Arkansas Coding Academy work for either Axiom or Merkle, which are both data vendors. That was really Axiom's whole deal, was aggregating data from credit reports and banking, credit cards and whatnot, and developing a profile of you. And now, if you're willing to pay for it, you can get all kinds of good information from these folks. Um, there's primary, secondary markets, and sure enough, if you want it, you can pay for it. But then there's also uh, like survey data that but you have to pay for it. It's not the polling company or whatever paid to gather it, so they're going to get some money to get it back from you. What I've seen is often is a subscription model where you have access to their database because you pay a monthly subscription, and it gets updated all the time. And then there's academic and research institutions that are always throwing stuff out there, like Pew and Gartner, and um, academic magazines will do polls and they'll release the raw data. And then I don't think any of you guys are in manufacturing necessarily, but we were at ACDS. We were speaking with somebody who owns a large chemical plant in southern Arkansas, and he was talking about hundreds of sensors and um, yeah, sensors, I guess, in the chemical plant process that were kicking out pressures and temperatures and all that, in addition to like maintenance data and whatnot, and time, and volume levels of chemicals and stuff that's been. Anyway, he was trying to make sense of all that data. He didn't really have any real analytic capability. They monitored things, but then they just kind of went on. And he was hoping to do some predictive analytics based on maintenance cycles and breakdowns of particular equipment. Um, but then outside of your connected factory or manufacturing 2.0 environment, just a staggering amount of data coming off of traditional network devices. I've had a GlaxoSmithKline cyber security guys in a couple of different cohorts before, and yeah, they got log files coming off of all the devices, workstations, firewalls, servers, that they have to sift through because it's all interconnected, the activity on the network. There's a site out there if you're interested in learning more, and even maybe almost like competing and getting your analytical chops known out there, is Kaggle. It's almost like a Facebook for data nerds, and there are I know they do contests every once in a while, and the winner gets an automatic job interview with a company. But they have data sets out there. Some are tried and true and historic, like the survivors of the Titanic. But then there's other, I don't know, there's thousands of data sets out on Kaggle. And then DIY. Sometimes you got to do it yourself. Sometimes you don't have the data you need, or it's so dirty that you wind up fat fingering in your own data. So there you go, sources of data. And we've already, like I said, we've already talked about all that. Some and these are mostly like file formats that I'm talking about, not really data, not data types. I was going to go into that next. Flat files. That term is derived because there's no hierarchy of the data. That's when you got like a good old fashioned CSV or Excel worksheet, and there's no subdivision and hierarchy of the data like you can do in some of the other data file formats. Flat file, CSV, tab delimited. The fixed length is still being used out there. It's really big in Arkansas state government reporting. Like the colleges, when they're reporting these thousands of students that are on grants and whatnot, they have to, there's the state publishes a data dictionary that tells you the, character 1 through 20 is last name and 21 through 30 is first name or whatever. And that's the room that you get. And that's that. And it is literally fixed length. And then of course you got data in more uh, proprietary formats like XLS or a Power BI project file or what have you. XML and JSON are JavaScript object notation, are the kind of the data format of the web. And it came in my memory back in the mid 90s, came in as a way for websites to transfer data from the back end to the actual web page. And those are both key value pair data formats, where you'll have like name colon Don, birthday colon April 8th, 64, so that the data is self-describing. And it can be nested so you can have that hierarchy. I worked just a little bit with Google Maps API, and it returns values in a JSON file that are hierarchical like that, and you kind of have to parse through it to get to what down to the level that you need. You got relational data. We'll spend a couple of weeks on relational database management system design and SQL querying. And it, to me, there are folks that get well into SQL that don't understand the underlying, first, second, third normal form, and databases they pull up aren't normalized, aren't really structured right. So and then there's all kinds of unstructured data out there, and that's kind of free form. Image, you hear about, in big data, unstructured data, it's images. Some of that will have structured metadata about the image, like the date and size, whatnot, maybe location, and text, because it's generally unstructured. It can be structured, but like I'm talking like an academic paper, or a blog entry, or the social media review post. There's a lot of information in there, but it's not structured very well. So there's a lot of work in computer science going into pulling stuff out of there. APIs are I would say rigorously formatted, but within the stuff, within the field that you pull back out of the API, you can get unstructured data like a Google review. And I've got a notebook for that. But an API Stands for Application Programming Interface, right? Application, not programmer, or programming interface. And that's just an established standard kind of web convention where you can expose the data via the internet, via TCP/IP, as long as the requester asks for it in the correct format and is ready to catch the data from your API correctly. It works, and it's virtually every social media site, Facebook, Twitter for sure. There's an API, Kevin, I know for Intellex. Did you tell me you were working with that API at all?
We do use it to like query some of the indicators that our clients put in.
Yeah, it's I know I found the user documentation for the Intellex API. I'm sorry, that the Intellex is the software as a service application that Kevin supports. I know I found the user documentation for that API that tells you what data can be retrieved and in what format. And when I was working with Don Tribble that was right after I got hired. So yeah, it's APIs are really no more cosmic than like an object-oriented method that takes parameters and returns, or a function, a subroutine that returns function. It's just that it happens over the web, generally speaking. So those are really handy. You can get, some of them are free, some of them are paid. But it's a way to get data out of a system and directly into your program without that intermediate human step of logging into the system, downloading a CSV, ingesting that CSV into whatever. You can do it all in one step, kind of, if you grab that data using an API. And then so these are kind of data file formats, but then there's different data types in computer science. You've got binary, it's either 1 or 0. Numeric can be integer or floating. String can be short, like a 64 character string, or it could be up to megabits large. Depends on the system. Depends on the data repository, the database. Date and time, date time data types tend to be the most difficult to work with in my experience. Am I sharing my screen, guys? Yeah. I am, right? Yeah. Okay. Good grief. I'm just looking at my PowerPoint. Because computers handle ones and zeros okay, and you group together ones and zeros to form an integer, and they seem to be okay with that. But dates and times are like an interpretation of a bunch of stuff for the computer at the operating system level, and it just seems that they all store things differently, and they use different formats when you're transferring between systems. I don't know. I have the most trouble dorking around with date and time, but they all handle it. It just seems to give me the most trouble. And then when we are dealing with data, there are three main categories of basic data types. Categorical data is literally putting something into a category. Could be like the species of penguins. I've got a data set I play with that's from observing penguins in the Antarctic. And there's 3 species of penguins, and that's it. You're in one category or the other. And I think I'm getting ahead of myself. So those categories can either be all even, where neither is better than the other. That's nominal. So like color categories, if yellow is not even any better than orange, then okay, they're nominal. But sometimes categories are there's a ranked precedence to them, or an importance of them, like grade. You might be in the D student category, which is not as good as the A student category. That was the case for me many times. So yeah, nominal and ordinal. And then you've got numerical data that can either be discrete, like Boolean data, binary data, 1 or 0, where there is, in theoretically, there is no value between the 2 data points. It's discrete. It's this, or it's that, or it's the next one. Or there's continuous, where in theory, again, there's a continuous number line. But you see integer data, which I guess theoretically is discrete. It's either 1, 2, or 3, and so on. But you can do the same kind of correlation and line charts and whatnot, with integer data, even though it's not technically continuous. And then you've got, again, date time, and within these all and you would add I guess I'm thinking string. This is just hitting me now. I've used this slide 3 or 4 times. There's just good old fashioned string data. And then there's subtypes, and it depends on the application. And we'll learn how Python treats those differently than Excel, which is slightly different than Power BI and DAX expressions, and slightly different than the different RDBMSs call them different names. And that's why I've constantly got a Google window open, because I cannot remember the format of all of these things. Okay, and we've already done this discussion part. I appreciate everybody. Everybody gave me some good feedback, and we'll build on those discussions. I appreciate you giving me a window into the data that you're learning. But I think I got all this kind of stuff answered. Any questions or comments to each other before we move on to the next one? Y'all are still with me, right? Edgar, you still there?
Yeah, I'm still here.
All right, buddy. I appreciate it. Sometimes when I see muted microphones and profile pictures, I start to feel lonely out here in cyberspace. All right, no questions. Pretty straightforward stuff, guys. Just want to make sure we're all using the same vocabulary. So let me close that one. Okay. And got another 20 minutes before the first break. So we'll do, yeah, just real quick. We'll, shirt on. We'll cover descriptive stats. Okay. So here we go. Some definitions. Some of this you may have never heard of. I hit the tutorials all the time, because this stuff is difficult to remember unless you're a statistician and you're using it all the time. I sat in on actually paid for a 2-hour training course yesterday, conducted by a guy named Wayne Winston. He's actually Googleable. got his PhD in 1975 and consults for IBM, the Dallas Mavericks. So he got his PhD in 75, which normally people are, at least 25 or so when they get their so anyway, he's white-haired old dude, but man, he was sharp. And it was an Excel forecasting and predictive analytics with Excel. 2 hours nonstop, wasn't hands-on. There's no way I could have kept up with him, but this guy was blasting through predictive analytics and statistics and probability theory and all of that stuff like a madman. I mean, he sounded like an energetic 35-year-old. He's got to be 70 something. Just fantastic. He's got a course on LinkedIn Learning if you have access to that, and he's authored quite a few books on statistics. Wayne Winston. Yeah, couldn't believe it. He's a professor at a couple of places. Indiana is his main, Indiana University. So yeah, quite the dude. So okay, so this is descriptive statistics, which is the easy part, easier half. So statistics defined by the OED, practice collecting and analyzing numerical data in large quantities, which is what all of you guys do. It's what we do generally. But check it out, especially for the purpose of inferring proportions in a whole from those in a representative sample, which is, taking a sample from a population, from a larger population, and then coming up with, a level of confidence as to how much or how well that sample, what are the chances, the probability that that sample reflects the larger population. And there's a whole lot of math involved in all of that, but there are, like anything else, there's calculators. You can plug in the size of your population and the confidence level that you want and whatnot, and it'll tell you how many surveys you have to get back, or how many times you have to run a simulation, or whatever the case may be, to get a representative sample. And there's a lot of theory in calculus and probability and sampling theory and randomness, and how random is a random number. Is it random enough? And so anyway, it is reliant on data quality, and interpretation is critical. I have a really good slide on the next in the next deck here that talks about that. And then there's two main branches. Oh, beg your pardon, I am drying out. Descriptive statistics, which tell you all about the data as you see it without doing that inferential side, which is inferring how much it reflects a larger population. Where you apparently you all, and I think all 40 other apprentices that are taking this course deal exclusively with descriptive statistics. If there's anybody in your company that is doing inferential, like, they sampled 100 user accounts out of your 2 million users, and drew some conclusion about all of them because they didn't feel like looking at 2 million data pieces of data. If somebody's doing it, it's somebody else. I haven't had an apprentice come in yet and tell me how they need to use inferential statistics. So I don't generally deal with it too much. I've had a 2-hour more extended talk about it twice in previous cohorts, but I don't think there's a need for it, so I think I'll avoid it. But based on your replies, you're all doing lots and lots and lots of descriptive statistics. You're describing the data using standard measures. So descriptive statistics, particularly single variable, it's fundamental to the data that you're looking at. So generally speaking, it gives you an idea of what's going on in your data, and you need to know this stuff, these things about any column, any data item that you're attribute that you're dealing with. So there you got measures of central tendency, mean, mode, median, but then you've got the minimum value, the maximum value, max minus min. It gives you your range in numbers. Variance and standard deviation tell you how spread out your data is. Skewed data is when it doesn't quite fit nice under the bell curve, where you've got equal amounts of data on either side of the mean. It can be skewed to one side or the other. Kurtosis is the flatness. I got a chart on all this. So yeah, I think all of you are looking at the mean is the arithmetic average. In fact, in Excel, they don't use the function isn't called the mean of a column. It's called the average of a column. So yeah, that's when everybody says, well, on average, that's what they're talking about. You take you add up everything in the column and divide by the number of items, and you get your mean. Median is in a perfectly symmetrical data set, median equals mean, but we all know there's a lot of types of data where you need to take the middle. This is the central data value in a sorted list of values. And for an even number, you take the mean of the two in the middle. And median, you very often see like median income, median housing prices, because a few super rich millionaires in your neighborhood can make the mean housing price worthless, because you've got 1,000 houses that range from 300 to 400,000, and then you've got Bill Gates and his $60 million house can completely screw up the mean. So sometimes median is more useful, and mode is the most generally in categorical data, discrete data. The mode is the most prevalent value. The like if you took a poll and people had to choose between strawberry, chocolate, and vanilla, whichever one of those flavors that everybody chose most would be the mode. A la mode. Get it? Okay. You're right, Edgar. That is tier worthy. Sorry, guys. I gotta keep it a little bit light, or I will fall off the deep edge. So yeah, mode. It's kind of like the average in a categorical sense. Okay. So why do we have three measures? We'll look at some charts that'll kind of show that. So like I said, in many of my chart packs here, my PowerPoint presentations, I post where I'm getting this stuff, my source, and sometimes the information underneath there. So if something rang a bell and you want to go back, there's a lot of tutorial sites in here that really help with these sorts of things. Okay, so the first thing, as far as visualizing continuous data or data, is a histogram. And this is a histogram. Looks like a bar chart, but it's not. A histogram, each of these bars are bins, and the x-axis along the bottom tells you the bounds of the bin, and the y-axis going up the left-hand side tells you how many observations, how many rows fit in that bin. So you can kind of start to look at your data and how it's shaped, because those bins will reflect that. Now, for instance, here, even though it looks like you kind of might have two humps, generally speaking, this is fairly fairly normal, fairly symmetric, and with a mean of 100.67 right there in the middle of the data set. That's pretty close to normal data. But then, like, sometimes you'll do a histogram of your data, and it is skewed, and the skewness, has a score, and it's important because if you try to do certain things with that skewed data, it doesn't fit very well. Like sometimes correlation, if you're looking at two variables together, if one of them is widely skewed, it will kind of goof up your visualization. And it's got its own measure. And then you've got a categorical data where you can't really do a histogram so much. So bar chart, breaking it down by category, will show you the relative frequency of those categorical observations. And of course, the tallest one, it shows you the number of people that said chocolate, the number of people that said vanilla, kind of like a histogram. But again, that's your central tendency measure for categorical data. And then you've got measures of variability, how spread out is a given data item. Your range, and that's just the max minus the min. There's a range function in Excel. Variance is and standard deviation are mathematically linked. Variance is how far the values are spread out, and standard deviation is a positive number that reflects the average distance of all points from the mean, and you just take the square root of the variance for that one. So yeah, we talk about things in terms of standard deviations away from the mean. So here's the math, and you never do this. No one ever does this outside of the first maybe exercise, where if they make you show your work in Stats 101, there's a dev function, or in every piece of software that will do this math for you. But then one thing that may or may not come in handy is z-score, is how far above or below the mean a particular data point is in terms of standard deviations, not in terms of the data measurement itself. Standard deviation is in terms of the data, like the average age of attendees in this course is, say, 30, with a standard deviation of 2 years. So the mean is 30, standard deviation is 2. I just made that up. I don't know how old you guys are. So standard deviation is in terms of the data item itself. Z-score is in terms of standard deviations, which plays into a lot as far as the likelihood of something happening. Normal data, things that generally will occur in nature are virtually always going to be observed in normal. Like if you looked at the height of trees, the height of the trees in the Ozark National Forest, it would be normally distributed. If you took enough measurements, 1,000 measurements of people's age, things that are naturally occurring generally fit the normal distribution. And in terms of standard deviation and the bell curve, this chart, can you go, let me make that a little bit bigger. And this goes into some calculus and some probability theory. But according to this, the theoretical construct, 68% of the observations will be within one standard deviation of the mean, regardless of what that measurement is. Will 68% will be in one. So it's 68, 95, 99, 7 are the three numbers to remember. The chances, the probability of being outside of three standard deviations or having a z-score greater than 3 it's 0.3%. So if somebody's outside of three standard deviations in something, in height or in IQ or whatever, either positive or negative, they are way outside of the mainstream. They're 3 in 1,000. And this, like I said, this goes into the whole inferential part. The chances of something coming outside of 1, 2, 3, what is your confidence level? You'll see 95% used a lot, 95% as a confidence level. That this is statistically, significant, and the results didn't occur by chance, because it's 2 standard deviations. The chance, so it's 5% are outside of 2 standard deviations of the median. Okay, so like I said, there's any number of, if you're using this stuff, there's any number of courses out there that will move you from these basic measures into that whole inferential side. Skewness is where the median and the mean are no longer in the same place because the data's skewed to the right or to the left. And it's kind of counterintuitive to me, but left skewed or negative skewness is got the hump on the right, and right skewed or positive skewness has the hump on the left, which, like I said, does not add up to me. Intuitively, I would think it's the other way around, but it's not. Okay, so we got 9:16. Let's catch break for 14 minutes. I'll see you back at 9:30. All right, we'll get started again. Any questions or comments? I'm kind of blasting through this because I think it's review for most. All right, go back to where I was there with skewness. Again, if this comes up at work, there's infinite amount of information out there on the internet, and I'd love to hear about it, because I don't generally get to, but I got to cover it, right? Because this is a data analysis course, and if they found out that you took a data analysis course and you didn't talk about statistics, I'd get in trouble. So we got to cover it. Okay, so yeah, skewness means how far the data concentrates away from being symmetrical. Kurtosis is the other. So that's like the horizontal dimension. Kurtosis is the vertical dimension. How humped it is, lumped it is closer to the mean or further away, or how many standard deviations, how likely it is that the data has more stuff outside of three, more occurrences outside of three standard deviations. So here's a good graphic on that. The normal distribution is the orange one in the middle. And then you've got leptokurtic and platykurtic distribution. I don't know why I can't say those words without bringing out my Dr. Evil impression, but for some reason, leptokurtic sounds like something Dr. Evil would say. Pinky to the mouth. Yeah, it's the tendency of the data to be centralized or more spread out than the normal distribution. And while we're talking about the normal distribution, there's a phenomenon, like if you took observations outside of an elementary school, say, and you'd see a bunch of kids between the ages of, you'd have a bunch of observations where age was between, say, 5 and 11. But every once in a while, you'd see a teacher or a parent or whatever, so that would account for the other observations. But the data would be skewed. It'd be skewed towards young because there's more students than there are crossing guards and parents and students, say. So that's an example of skewed data. But so you took 100 observations and it was skewed to the left. So what, positively skewed. But there's an element in inferential statistics called the central limit theorem, where if you did that same thing, whatever, 50 times, where you looked and counted the age of 100 people, but you did it 50 different times, the mean of those 50 samples would be normally distributed, even though the underlying data set is or set of observations is skewed. Over time, the observations would still be normally distributed. So like I said, that's back to Stats 101. Some of you guys have had that, others haven't, but just to me, that's a kind of an interesting, I remember that from undergrad stats 25, 27 years ago, 28 years ago. Good grief, I'm getting old. And of course, the shape of the histogram will tell you a lot about the data. Upper left-hand corner is normal. The next two on the top row are skewed data. Sometimes you'll have data that's uniformly distributed, where you'll have exactly the same number of observations inside of a data set, but it's pretty rare. The next in the middle are bimodal distributions. That might be something that would happen, like so yeah, back to our kindergarten or our elementary school observation. If you looked at every human being you saw from 15 minutes before school started up until 2 minutes after the bell rang, and looked at every human being you could observe, you might see a bimodal distribution. You might see the 7-year-old kid get out of mom's van or dad's truck and run into the school. So you'd start to see a pretty clear double, and you might see a teacher welcoming everyone to school, and you might see a crossing guard, an adult crossing guard. So that's where you might get a bimodal distribution. Or like if you were to look at I don't know, maybe average body weight of humans, you might see that there's a bimodal distribution between women and men, maybe. So anyway, that's what it means, is that the data has two um, means almost. And if you took the mean, it can kind of, and without looking at the data, that's what I'm saying, it can kind of skew it. So I got a really good chart on that in the next presentation. And then our spread, or our kurtosis. Yeah, and again, I got all this from you guys. But we didn't talk about skewed data and outliers. If you see something that's way outside of, like, you do a histogram and you got one that's way outside, up or down, what would you do about that? So Seth, you look at this kind of stuff at the campaign performance and whatnot. What's your approach when you see an outlier?
I usually try to figure out why it's happening. Like, we run 3 quarterly promotions and 1 yearly promotion. And so when I'm looking at those quarterly promotions, I remove like the signups from the yearly promotion. Like if I'm looking at sign up numbers, right? Like participant numbers,
Mhm.
because there's going to be far fewer in that one. There are far fewer people who sign up for the year long promotion than there are the people who sign up for the quarterly promotion. So including them in when I'm trying to figure out like how well the promotion is doing kind of throws it off.
Gotcha. Yeah. Oh yeah. That would. Yeah. Absolutely. That's almost like analyzing apples and oranges, because you're right. An annual subscriber might be a completely different type of customer than a quarterly subscriber.
Yeah, they're generally like bigger manufacturers or things like that that have other things going on that don't want to track something like quarterly like this. They just want to get a number at the end of the year, and that's what they'll get back from the promotion. So when I'm looking at things like that, I remove them from my spreadsheets or whatever.
Gotcha. And if you're looking, if you're looking at performance of stores, what stuff is selling well or whatever, I would think an outlier, good or bad, would cause investigation as to why that happened. If you had, a store manager, say a general manager at Chili's, you're back at Chili's headquarters looking at a store level data, and there was a manager that was uh, well outside the norm, maybe outside 2 standard deviations, at keeping employer costs or employee costs low, keeping salary overhead low, or the other direction. They were I guess depending on how you look at it, it's positive or negative. But anyway, yeah, if you see something happening that's performance based, and it looks, wow, that looks really good, you might investigate it. Might be somebody's fudging the numbers. It might be that somebody's really, really, really good, and you need to duplicate what that person is doing, or what that process accomplished, and vice versa. So outliers can be really helpful, um, identifying good and bad performance. So there you go. Okay, cool. So yeah, descriptive stats, just what the data says, without saying, okay, well, if I looked at 10, that must mean the whole, the it's going to play for the whole 1,000. There's a whole science involved in deriving meaning to a larger population from a limited sample. All right. So let me get rid of that one. And I wanted to talk about, do you want to save your changes? Sure. I didn't know I changed anything, but okay. And then next one, that was looking at a single, those measures were looking at a single variable in respect to itself, like, age, or even if you took 2 variables which is the next thing I wanted to talk about. Bivariate statistics was just looking at two variables alongside each other. Even if you took two variables and turn them into a rate or a ratio, like you very often want to know average number of average, which is a univariate statistic, right? A descriptive statistic of numbers of items purchased per customer, say, or transactions per hour. Like there's rates and ratios. A rate is just a ratio of something over time or per time period. But you can still turn those two transactions and time period, you can turn that into a single data item and still look at it in a unit. That one ratio is now back to being a single variable. So anyway, I wanted to talk a little bit about this because we will do some of this as well. Bivariate is just looking at two variables. Generally speaking, you look at the X and the Y. Generally speaking, when you're looking at two variables, it's important for the tools to work and to meet convention and to make it look like everybody's expecting that the X variable is your independent variable, the thing that explains the change in Y going up the vertical. So the horizontal is the thing that you don't really have control over or independent variable, and Y is the response to the X. So you always talk about changes in Y over changes in X. And if you get those backwards on a chart or in your mind or whatever, it can cause you trouble. So as we go through the course, we'll think about that. But Y is otherwise known as the dependent variable, because the change in Y depends on the change in X. And if you're doing an experiment and Y doesn't seem to have any correlation to the change in X, then, obviously you didn't get the expected result. So the outcome or the response variable. So when you're doing like a scatter plot or experimental design, you got to keep those two in mind. And there are slightly different statistical tests for significance and visualization for these different combinations of data types. So you've got a categorical variable for X, like men and women, or smoker, non-smoker, or education level, up to including high school, college, postdoctorate, whatever. So you've got categorical data for X, and then you look at how that explains something, how that affects something on the Y-axis. Could be like this example here, whether or not you got the pill or you got the placebo, and the effect on, if it's a blood pressure medication test, what was the effect on blood pressure between the real drug and the placebo. And a side-by-side box plot. If you haven't seen a box plot, I'll show you that here in a minute. Statistical tests for significance, again, that goes into the inferential. I won't go into that. So then sometimes you've got two categorical variables, like X is whether you were a smoker or not, smoker, non-smoker. And then the y-axis would be, did you know, the count of people that got cancer that were smokers versus the count of people that got cancer that were non-smokers. And that's where you can start to do, you know, like a ratio, like you're 8 times as likely to have gotten cancer if you're a smoker, because there's, you know, in the sample, 8 times as many smokers wound up getting cancer as non-smokers. So side-by-side bar chart or a stacked bar chart, and we'll go into chart types also. And then you've got your maybe the one that you think of the most, where both are numeric or, you know, continuous, but numeric really. So like, for instance, X would be your income, your annual income, say, from 0 to whatever. And Y would be the average hours per week watching TV, or it could be, you know, the price of your car. Generally speaking, the more money you make, the more you spend on your car. So you start to see where they correlate in a scatter plot. And the test of those two being together is Pearson's correlation coefficient, or a number that you see in a lot of equations. R is the symbol for it. So that's the one that you see the most of. Any questions on that? I got a graph on each of those coming up. Questions or comments on any of those? So that's looking at 2 variables together. So yeah, Pearson's R will tell you how closely things correlate, and kind of the confidence that you can put into a linear regression. So if you got the equation for the line of best fit and you plugged in the numbers, when X increases, we get a 0.65 or 0.9. R is between -1 and 1. Often people will use R squared because it's always positive and it shows correlation, even if it's a negative correlation. So a negative R would be, you square it, you always get a positive R square, and that gets used in some applications. But yeah, super simple linear regression. The you can do it manually, but no one does. The software will tell you the whole y equals mx plus b equation, and you plug in an x, and it'll give you like a projected y, but the strength of the correlation will give you a confidence level as to whether or not that's actually going to happen. Because a low correlation, you got 0 confidence that you can actually project anything using linear regression. So here is our first example where we've got these are called box and whisker diagrams, and I'll go into this more in chart types. But each one of these, they've got 3 blue ones and 3 red ones. Each one of these is a box and whisker, where it real quickly visually it gives you several clues about the data in one quick little diagram, one quick little icon. So over here on the far left, you've got that blue box and whisker, right? So you see the box, and then inside the box, there is a line separating the top half from the bottom half. Well, that line is the median. I'm sorry, the mean. The mean. The edges of the box are the quartile, first and third quartile, and the whisker shows you kind of the tails. So if you did a histogram of that particular data in and of itself, you'd see kind of the same shape, only a box and whisker kind of turns it on its side. Well, you can do them horizontally too, but it gives you the kind of the same information in a slightly different format so that they can be looked at side by side. You couldn't really do histograms of this stuff and look at them next to each other like we can here. But that's what that box and whisker is kind of intended to represent, is the distribution of the data. Where's the center and how spread out is it, positive or negative from the center. So this blue one over here, we've got categories of before and after. So this is our placebo, and we're also grouping them into categories of age by 30 to 45 and 46, 59 and 60 plus. So you've actually got double groupings here. But before, this is before the medication, after the medication. So you see, this is the graph of that blood pressure drug test. So before, this was your data before and after for folks in age 30 to 45. And then before and after for middle-aged folks like myself in the middle, and then before and after for older people. And you can see even before the drug trial, just when they took the preliminary measurements, your average blood pressure went up from what, 148, and then in the middle it's a little bit higher because the older you get, invariably that blood pressure goes up. But then you can see that the medicine had a slightly better impact on average blood pressure in the younger groups than it did in the older group. And they slice and dice this data. When they do a medical trial, they slice and dice this stuff 19 ways to Sunday to see what the effect is on different groups of people by age, different groups of people by sex, to see the before and after impact. So this is a way to look at categorical data along the X and the impact of numerically on the Y. Okay, and then we got categorical on the X and numerical here, and just a simple two categories: smoker and whether or not they got cancer. So you can see most people that smoke did not get cancer, right? I mean, under smoker, not everybody got cancer. But anyway, this is how you would look at those two categories with it, and then a numeric result. This is the number of observations on the left here. And then classically, you're looking at two numeric variables and how they correlate. And that's got an actual score to it that you can use, or R squared. I drew this scatter plot in Excel and pasted it in PowerPoint, and I used population, which increased for Arkansas, which increased over time, and the number of violent crimes committed. And as you would think, more people, more crime. But you don't assume that there's going to be an effect like this. But I wanted to use one that was that had a high R score. So yeah, as we get more people, we get more crimes. So to be fair, you would always look at crimes per capita. You know what I mean? You would always look at something like this. You wouldn't look at it in raw numbers, like COVID cases. I saw on TV or I think it might have been like a late night comic was talking about how Australia, we had 10 times the cases, the COVID cases that Australia had. Well, if we had 10 times per capita, that's, something to look at. But if we just had 10 times the cases, there's only 25 million people in Australia. So that's not fair. So anyway, correlation. This is how closely related, how well a change in X predicts a change in Y. And the higher the R squared or R value, the more closely they're correlated. Actually, the higher the R squared value, and it's between 0 and 1. Because you can have negative correlation. You can have things going down, which might be good as X increases. So a negative correlation could be what you're looking for. It might be a good sign. But it's the same math. What they're looking at here is the average distance of each data point above and below this theoretical line of best fit. And then you square it, because if you actually looked at them and didn't square it, it would be 0, because they cancel each other out mathematically as you look above and beyond and do that scoring. But any correlation, anytime you see R squared above 0.8, it's a strong correlation. But anything above 0.5 is positively correlated, so it's worthy investigation. You start seeing things, you start seeing an R squared down in the 0.1, 0.2, then there's no confidence or little confidence that X predicts the change in Y. They're not correlated. They don't have any cause and effect whatsoever. And even though they're correlated, they don't necessarily have cause. Have you guys heard that term? Correlation does not determine causation. Just because two things are mathematically correlated doesn't mean one causes the other. I think we've got some examples of that as we go through the course. And I just pulled this in today. I wanted to show you how these descriptive stats can be misleading or confusing. And a visualization might be the only way for you to kind of see what's really going on with the data. This is kind of a famous, has anybody heard of this before? Anscombe's quartet. Any of y'all remember that from previous training?
I think I haven't heard of it.
Doesn't sound familiar. Well, good. Okay, so I'm sorry, Dexter.
No, sir, I haven't heard of it before.
Cool. I had not either, and I had statistics. I hadn't heard of this until I started learning data analysis with Python, and my buddy Mike Ellis uses it to show why visualization is so important. Because what we got here are 4 different sets of data in the lower right corner. You've got an X and Y, and I think there's 11 in each one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So there's 11 observations or 11 rows in each of these 4 data sets. And this is from a statistician. It's not real world or whatever. It's used to illustrate the point. Okay, so for those 4 data points, the mean of X, the descriptive statistics are the same. So you would look at it and you would think, by just being a strict adherent to the descriptive statistics and the R value, that you were looking at the exact same data. You might even think it was duplicate, because even though but look at the graphs, the mean is the same, the variance is the same, the mean of x and y, and the variance is really close in both x's and y's. The correlation is identical. It's they are correlated mathematically, the same 0.816, which is significant. You would think there was a strong relationship between the two. But you can see here that a simple linear line of best fit doesn't work, and that the data sets are pretty different. In the upper left hand corner, you've got a scatter plot where there's obviously some relation, obviously, but it's nowhere near as tight as the bottom left corner. Look at the graph in the bottom left quadrant. They're super tightly grouped. And then you've got I don't know if that'd be reverse exponential or logarithmic or what you'd call that upper right graph, where it goes up like a candy cane and then dies off. It's got the exact same line of best fit. It's got the same correlation, but you can tell that as X increases, you're going to start to have a diminish in Y. And that you'll see that very often in that where it goes up, and this is going to be company value. It's going to be annual sales volume as they grow and grow. Yay, everything's great. But eventually you got diminishing returns. You can't keep growing at that rate forever, right? So you'll see this where it starts to die off, and then it won't go all the way back down to zero. It'll kind of flatten out and then increase a little bit more, and it kind of makes this S curve, it's called. And you see that in company growth numbers all the time. It was an excellent example in that workshop I was in yesterday. And there are other lines of best fit that we can use, like in Excel, that will give you an equation that is better, more accurate at doing a projection, because it's not unrealistically linear. Even though you got a high correlation, you can't trust that the equation of line of best fit as a linear thing, and then look at the lower right data. I mean, that nothing happens in Y except going straight up. So there's it's correlated, but that's the goofiest relationship you could ever think of. Anyway, it's goofy looking as far as scatter plots go. And it's almost like random when X gets to 8, or X is 7.5 in all of them, I think, or close to it. Where are we? I'm sorry, the Y is like 7. No, the X in number 4. Yeah, it's 8 in the entire data set, except for 1, which is 19. So bam, all of a sudden there's your outlier. And that single outlier is enough to hose up the descriptive statistics and give you the same descriptive statistics as all the other ones. So this is just a good example of why you can't trust linear regression strictly. There's just a lot of art involved in interpreting. I think we had that at the beginning of one of the slides, interpreting the data. Any questions, comments? You guys seeing this kind of stuff? Did I get anything backwards or confuse anything? Like I said, I'm more of an application developer than an analyst per se, really, at heart, in my heart of hearts. All righty then. Well, I think we're going to blast through class a little early today. I wanted to go through a Jupyter notebook today, but then I think I'm going to let you go. So we're going to rock on through break time would be in 10 minutes, but I'm going to finish up a Jupyter notebook, that Jupyter notebook number 2 that I talked about. Because I want to get by the end of or on Thursday this week, I want to be able to do some Python word problems to get you guys programming and solving problems and turning in IPYNB files to the classroom. So we'll stop sharing that and move on to, let me close that down. Sure, save it. And so share tab. There we go. Okay, everybody seeing my notebook too?
Yes.
Okay, guys.
Yeah.
So again, this is elementary, shouldn't take very long. But remember, no matter how complicated a chunk of code gets, there are 3 basic statements, 3 types of statements: sequential, decision, and repetition. This notebook, I just wanted to hone in on the input and output, because some of the programs that you'll write, I'll ask you to gather input from the user, and that uses a function called input. So you need to make sure you got that. Input gathers input from the user from the keyboard, and print puts it out to the screen. So you'll use that a lot. Okay, so I hit cell all output clear. I don't remember if I cleared this before I loaded it up to the classroom or not, but that's what we got here. Okay, so screen IO, remember we got the print statement. And there are, print can get complicated. There's a lot of documentation out there. The formatting, particularly formatting numbers inside of a print statement, can get a little complicated, and the formatting, it's called a mask when you tell it, like a date mask dd/mm/yyyy. That means you're going to take the data and format it as that traditional date format. Well, the format masking in Python can get a little complicated. Oh, one other thing I did not mention before is that Python strings can be enclosed in either double or single quotes, and that double and single quote can be mixed and matched. I would pick whatever you're most comfortable with. For what I guess it's because I learned, and I'm sure in Pascal you had to have double quotes around a string or it would barf. But you can use single quotes, and I'll prove that here. The single quote next to your enter key. And this is a notebookism. Watch this. I'm hitting one time. I'm hitting the quote key, and it sticks in double quotes for you, and it thinks it's being nice. And this is a function of Jupyter Notebook. It does formatting for you that is context sensitive, and it predicts that if you put in like an open parenthesis, that you're going to need a close parenthesis, right? So it sticks it right next to that. But sometimes you're going in after the fact, modifying a line of code that's already got all these parentheses, and you've already put the beginning one, and you go to put the end one, and it sticks it in there for you. So heads up. Buyer beware, whatever. But yeah, here's a notebookism. It inserted a closed quote, a closed single quote for me, even though I don't need it. I've never looked into it. I guess there may be a way to disable that, but I haven't looked into it. Just beware. So here I've got, you just get rid of the extra one. So here I've got single quotes. And if I hit Control Enter and run that, it makes a liar out of me. Oh, there you go. Because that's an apostrophe. Okay. And so there you go. We use double quotes if we need to put a single quote inside of a string, because it will not evaluate what's inside of those double quotes. But if we try and use single quote and there's an apostrophe, it'll error. I'd forgotten about that. That's an interesting Pythonism. So if we wanted to use, back to my original, we will not do the contraction. It has got sharp teeth. So here's your single, and in there, put the extra one in there again, put the close quote again. So yeah, you can use single quotes, or you can use double quotes. So pick whatever works for you and kind of stick to it. I by habit, I tend to use double quotes, even though I think it's extra. It's a shift double quote above single quote, because that's the way I learned, and that's the way I was taught, and old habits die hard and all of that. Generally, I would think if you work within a Python shop, they'll have a convention as to what people prefer, and you'll just work with that. Okay, so inside of print, you can send as many parameters as you want. There are functions that do that let you send a basically a list of parameters, and it will do something with that list no matter how many of them you send. But here in just a minute, we'll see that there are also named parameters that you can use that are optional. You don't have to use them, but you do have to send print. Actually, I don't think you have to send it anything. I think you can do open paren, close paren, but we'll check that there in just a minute. Like I said, there's pages of documentation just on print. So here's a line out of Alice in Wonderland, or the song White Rabbit, I guess. One pill makes you larger and one pill makes you small. By convention, we call the numeral 1 in that print statement, we call that a numeric literal. And text surrounded by quotes, we call that a string literal. Numeric literals can be either integer or floating point. So that's how you do that print. Now, here we got an example of a named parameter, a named optional parameter. We don't put, by default, print puts a new line. So it does everything at the end of a line. Oh, hang on a minute. I wanted to test that theory and remind myself. So I hit plus to get a new code cell, and I wanted to do print. And if I just hit the left open paren, bam, it sticks in the right open paren for me, which can be handy, which is nice. And like I said, just be aware of that. Now, if I run print without sending anything, what do I get? I do get a blank line. So print with no parameter at all is a blank line, but you can also send it a blank string, and it does the same thing. But yeah, print with no parameters just means print nothing but a new line character. Okay, so and equals, you can say there's nothing in there. That's quote, quote right there together. And equals quote, quote will suppress the new line character so that the next time you print something, it'll be on the same line. So it's going to say checking file integrity. Okay. And it could be, you might want to do that especially if you've got a process that takes a little while. Python, like I said, is not notoriously fast, and y'all are working with, larger and larger and larger and larger data sets. So it could be that you write some code that does a bunch of and you want the user to just kind of realize, this is going to take a minute. So you could say, processing your data, this could take us a few seconds. So this could take a minute. You see that in common use out there on the internets. So there's an example of doing that. But yeah, a named parameter within a function call. And we'll see in Python, there are lots and lots and lots of functions where you have optional named parameters that you can set equal to something. So I'm curious if we just said, and here's single quotes, right? You can mix and match them, like I said. I'm curious if we put end equals a character, asterisk, asterisk, asterisk. What do we get here? Yeah. So it replaces the new line character with whatever you put in between quotes. And if you put nothing, it replaces the new line character with nothing, and it doesn't go to the next line. All right. Print is actually a function, and we'll be using functions a lot. So yeah, if I mess up and call it a command, you're welcome to come off mute and say, it's not a command, Don, it's a function. Okay. So there's another, and this is not the way I would normally use this at all. But the input function is how you get data from the screen. And there are other optional parameters, but I never use them. And a good format for getting the user is to be standard. Let me fix this. This is ugly. I probably typed this quickly. Is to use a capital letter and a space after the colon so that the cursor is blinking with a blank space between the colon. And I'm sure that's because I learned it that way. So that's the way it should be, because that's the way I learned it. So yeah, when you prompt the user, you're going to want to use standard looking prompts. But what this is going to do, remember, functions are kind of like almost, it's like a mathematical expression. They resolve, or they occur, and you get the result from the inside out. So the innermost function of these two function calls is a call to the input function. So that one's going to occur first. So you're going to see the enter a value, and then that whatever I enter is going to get returned to the print function, which is the outermost function. So it'll print what I just input. And like I said, that's not something you normally do. So we'll do something more realistic here in just a sec. So I'm going to print that, enter a value. And you notice the star. I told you that inside of these square brackets, while it's processing, and right now it's going to sit there and be a star forever. While it's processing, you get a star. So until I enter a value, you're going to have that asterisk on there. And every once in a while that comes in handy. You can kind of see that something's hung, and you look down the screen and you forgot that you're actually inputting a variable. And that there's an input statement, and it's just waiting for you to enter something. That's on like a complicated notebook. So enter a value, could be anything. How's that? And then you print it out. Okay, I always error on the side of slow and steady. Sorry about that. Okay, so remember, this notebook is about sequential statements. So those are input, output, no decisions being made. It does it one time and then it's done. But we can also one of the things you'll do super frequently is assign a value to a variable, which we touched on last time. So here are 3 assignment statements, and remember the assignment is 1 equal sign in Python. In R, it's like a less than sign and the equal and the dash or something, less than sign and the dash. I think it's like an arrow pointing to put the value what's on the right hand side into the left hand side with an arrow. And I mean, so anyway, but Python usually is really intuitive. So yeah, as you would think, the assignment sign is equal, and I'll say it again because it's really easy to forget. When you're comparing to see if something is equal to something else, it's 2 equal signs. That's easy to forget. So we got a string literal being assigned a last name. We got an integer, and notice the color change. That's a Jupyter notebook-ism, where it formats things with different colors to kind of let you know what's going on. And there's kind of like a color code to this stuff. So string literals are being defaulted as red. Operators are purple. Numeric literals are green. Variables are black. The variable name itself is black. So once you get used to this color scheme, it kind of lets you know if you're typing in something wrongly. Sometimes you'll see it and it'll be like the wrong color, and you're like, that ain't right. So it helps. So we did 3 assignment statements, and we are going to remember Python is dynamically typed. Python will assign the initial data type of the variable based on its initial value. So we can use the type function, again, embedded within the print function. So we got a string literal here. The data type of last name is, and we're back to my favorite double quotes. The single quotes are legacies from my buddy Mike. He's a single quote guy. I'm a double quote guy. There you go. And then we will see the type, data type of these 3 variables in these 3 print statements. Okay. So you see here, we say the data type of last name is class str. So for the 2.5 of you that haven't had object-oriented programming theory, I'll introduce this here, and it may or may not sink in. If it doesn't, don't sweat it, because this is useful information, and it helps in understanding Python functionality and the functionality of other programming languages. But what that means is that last name is an object of the class string. Now, a class is a way to define a type of thing that you're going to use in your program. So probably something that everybody would relate to. I'll use a video game. So you're writing a video game, and at any point in time, based on player action or the game's rules, you can have a bad guy, a soldier, a character pop into the game. In programming, good old-fashioned, before object-oriented programming, you would have to write the if, then, else, and creating that character, and then getting rid of that character in memory and everything, all kind of sequentially. And it would get hairy. Those old programming languages were really good for things like opening up a file and doing some processing and writing a file back out and doing some logic and whatnot. But when it comes to programs like video games where you have these objects running around in the program, it really does help to have an extension to that programming language that lets you create like a template. That's what a class is. It's a template for something in your program. So say you have a character class, that character class will describe what a character can do, and it will describe attributes that the character might have. Think like the character has a type. It's either, you know, an animal or a person. And a person object could have health points. So at any given time, if you create one of those things, an object from that class, now that object can have attributes about it. It can have the amount of ammo it's carrying, the health points, which I don't know which team it's on, whatever. So it can have attributes, and then it can do things. It can take actions, and within object-oriented programming, you would declare those as, it's called a method of doing something, like run forward. So you would code up, you know, soldier 1 dot run forward 10 spaces or something. That's very simplistic, but that's how object-oriented programming works. When you do an assignment statement in Python, you're actually constructing an object of that class: float, string, integer. But there are many other, so there's classes of objects that are basic to the language, but then you can create your own class of things, and we'll see that as we get into data analysis. The your spreadsheet worksheet object, data frame object, is a class, and it can have attributes and it can have behaviors. It can have attributes and methods. So anyway, like I said, I wanted to introduce the concept of object-oriented programming, but we won't be writing our own classes here. But you've got to understand that when you're operating, say for instance, on a string, say I wanted to do something to last name, there is some functionality that's available in a built-in Python function like the print function. But there's some functionality that you would call, because it's a method of the string class, and you call a method with you put the name of your object, last underscore name, dot, and the method name. And it looks like a function call because it kind of is, but it's a function call on that last name class. And it can be, as you're learning Python, it's a Google away as to whether, is that a function or is that a method of that class? And you'll see yourself doing those sorts of searches. So anyway, no one has interrupted. Any questions on that?
No, sir.
I mean, if you're going to be doing object-oriented programming, you probably ought to take an object-oriented programming class, because it'll be a whole lot more thorough, excruciatingly thorough in covering object-oriented technology in computer science. Okay, so we got some more sequential statements down here. We're going to do a mathematic operation, dividing user height in centimeters over age to come up with average growth per year, and then we're going to print that out. So anything you do over here on the right will resolve to a value that gets assigned to the variable on the left. This can be the first time you ever use it, which we are here. Average growth per year. You can mention for the first time because you're declaring it as you use it in Python. But you can't do math on the right side with something that you've never declared because it doesn't know what you're talking about. So you'll see an error message. So here we're just doing a real simple assignment statement and then printing out the result. And we'll see here in a minute, division always resolves to being, or always defaults to a floating point object. And now back to our point about assigning the result of the input functions. Okay, so in the Python exercises, go ahead, Dexter.
Oh, nothing.
Okay,
I'm sorry.
that's right. In the Python exercises that I give you, I'll often ask you to write something that gets input from the user, and this is how you do that. So you do it in an assignment statement. So width equals, and then I'm doing embedded functions again here. I got an input statement that I am converting to int. So that makes it an integer value. Regardless of what I put in there, it converts it to integer. I want to say, input, it's in the notes up here in my comments. Input, regardless of what you type in, returns a string type, which will screw you up if you try and do regular mathematics on a string, because the numeral 2 as a string is different than the numeral 2 as an integer data type. So we always have to do, we're always doing conversions in Python. It just seems to be part of the game. And again, as an old programmer, counterintuitive, but that is the way it works. And it works well. You just got to remember to do it. So we are going to enter, we're going to, so that'll print out, enter integer rectangle width to the screen. And then whatever I type in, it will convert to integer. If I type in Don and I send it to the int function, it'll puke. So there's ways to error check that if you want to write a more robust program. Generally speaking, in this class, we'll write stuff so that if you put in what it's looking for, it'll work. That's good enough. But if you, we don't generally write user-proof code in the course. But there'll be a few examples where you can, like there's a function to check, like is numeric. So when somebody inputs something, you can say, if is numeric, you can send it to the int function. Even if it's floating point, it'll just truncate the decimal places, and it won't error. But if is numeric is false, then they put in something, and you got to say, sorry, you entered a non-numeric, and you got to do a while loop, and we'll talk about all that. So anyway, so we're doing 2 assignment statements based on the input statement that we are converting to an integer. That's how all that works. Remember, it resolves from inside to outside as you nest these functions together. And then we can print a string literal, comma, an arithmetic operation, which resolves down to being just a numeric literal. But you don't have to assign all that outside of the print statement if all you're doing is printing. And the area is length times width. And we've changed them to integer. So I'm going to say the width is I don't know, 12 and 23. So the perimeter 70 and the area is 276. So now I'm going to say if I what happens if I put in a floating point? 0.7. Bam, you can't int. There you go. You can't int if the user puts in a floating point. I was thinking it truncated it, but it does not. So if they put in the wrong data type to what you're looking for, you would have to, do some bounds checking for the data type, and you may ask them to enter something between 1 and 5. And if they enter 6, you need to put in the logic to loop back up and say, nope, sorry, that was out of bounds. Enter something between 1 and 5. So yeah, error proofing your input. I think wasn't that one of Mike's 8 rules of programming is all input is evil. Verify it until proven otherwise. So yeah, invalid literal for the int function. So generally speaking, Python data, Python error messages are fairly understandable. Sometimes not, particularly when you're using, complex statements and you're incorporating functionality from these external libraries. Man, it can be tough, which is a good reason to write tight modular code. Okay, so went over this before. We can do pretty much all the, any kind of math that you would think of, and the format is very much like Excel. So there's 2 that are less commonly used I want to talk about here. And like I said, we can run that. And so division returns a float data type, multiplication returns an integer, exponentiation of integers returns an integer. But there's a thing called floor division, which gives you the largest integer value beneath the result. And it's 2 slashes, // So 5//2, where 5 divided by 2 is 2.5. Floor division would be the lowest, would be the greatest integer lower than 2.5, which is 2. And that gets confusing when you start doing it, when you're dealing with negative numbers. Modulus, modulo, mod returns the remainder as an integer, which is really handy if you want to check if something is evenly divisible by something else. Like if you want it to be, if you're looping until something is, and you're doing something weird every time it's evenly divisible by 5, you would do variable mod 5 equals 0. If there is no remainder, that means it's evenly divisible by whatever you're modding, in this case 5, which can be really handy. A lot of times you'll see something mod 2, that means it's an even number. If something mod 2 equals 0, it's an even number. And a lot of times you want to do something based on evens versus odds. So yeah, floor division and mod are mathematical operators that you might not necessarily deal with frequently. But a lot of times you know what you want to do, and if you just Google it, oh, sure. Of course, there's a way to do that. It's something common that somebody would want to do. Okay. Now, just real quick before we're done, we will use, beg your pardon. We will use a fair amount of libraries in the course. And these are chunks of code. They are libraries of functionality that are on your workstation that came with Anaconda. So real quick here, when I'm done, I'll bring up Anaconda and show you some of the libraries that we're talking about. But in any given program, whether you're writing that script in an IDE like Spider or Eclipse, or it's in a Jupyter notebook, one tab on your browser. Once you import that library, it's in there. You only need to import it once. You don't need to do that import in every cell. So here we have the math library. Now in the base language, you don't need to import any libraries, as we have seen, to do basic math, but there are a whole lot of functions in math that are implemented for you in the math library that are not in the base language. I want to say things like, well, of course, we got square roots example here, but I want to say like the trigonometric functions, like if you're doing sine and cosine and tangent of things, those are not in those functions are not in the base language, like print and input and int. So you have to import that library to get that functionality. And there sometimes you use a different convention, but generally speaking, when you're calling a function inside of a library that you just imported, you use the name of the library dot the function so that it knows where to get it from, because it doesn't know to go look in every library that you've imported for functionality. So you have to you have to use library dot function name. So we'll run this. But then what you'll just real quick here, you can rename that library. Sometimes some of those libraries are kind of long names, and people will use a shortcut. Like I've told you, pandas, everybody calls PD. Seaborn, everybody calls SNS. So there are accepted conventions, but we could have called this import math as something longer, and I'm just showing you this as statement. Do some math, and then here I could call it math, or I could call it do some underscore math dot squirt. Let's see if this makes me wrong. There you go. So you can import a library and give it an alias. That's all that's talking about. Okay. So real quick, the math library. Let me cell all output clear. Make sure I didn't do anything goofy here that I'm not going to want to see next time. Okay, yeah. So hit the floppy disk to create a checkpoint, and then say File, Close, and Halt. We'll put away that tab. Okay, so stop sharing that, start sharing screen. And inside of your Anaconda, you'll see this Anaconda Navigator. And that's a GUI that will show you the libraries that you have installed on your computer. Anaconda installs got a couple hundred. But you can also go to the PowerShell, the Anaconda prompt, and you can install, and it knows to go out to the Anaconda repository on GitHub with that install command and grab whatever you're looking for. And this this will be of most use to you if you're getting into Python and you're maybe doing some tutorials that tell you you need this library or that library, but they're not they're not part of the Anaconda distribution. They didn't come with Anaconda. So this is the whoa. There's a new version of Navigator available. I would do that, but I don't want to remind me later. I don't want to slow down class because we're about done. So in here, you can have multiple environments where like some people really want to keep Python version 2 around because they've got a lot of code that isn't necessarily forward compatible. So they keep an environment that is the older version of Python. A lot of Python in version 3, which is what we're on now, I think 3.9, is backwards compatible, but not always. So some people will do that. I did an R environment so that if I can create a new notebook in either Python or R, and it will call a Python interpreter or an R interpreter on my computer either way. So there's multiple environments here, but inside of a given environment, you have these libraries here. These are all installed packages or libraries that you can say import. And this just gives you an idea of how much stuff is out there that isn't in the base language. This thing would be huge if Python had all of this functionality actually in the interpreter every time you ran Python, and it had to read all that up and have all that functionality. But I wanted to show you, like, for instance, Matplotlib is a mathematical plotting library that everybody that does data analysis with Python knows. Now I've got one. You see, it's a slightly different symbol here. That means I installed it. MariaDB is a library that lets you connect to a MariaDB, which is a offshoot of MySQL. So I had to go out and import that and download it. So yeah, this is your environment, your Python environment in a GUI environment. So 421 packages available, but you'll see most of them are installed base Python or base Anaconda. I'm sorry. I want to see Seaborn. Yeah, there's Seaborn. Selenium WebDriver lets you do automating web testing. They've got there's a library there. Just a ton of functionality. Scikit-learn is one of those that you've heard of for doing machine learning. So yeah, lots and lots and lots and lots of external libraries. Now, like math is part of the base Python library, but you have to import it. It's not an external package like these are. Slightly different. They operate the same. But anyway, there you go. That's what that Anaconda Navigator does. All right. So Thursday, we're going to do probably like basic chart types and notebook 3. Let me look real quick here. Any questions so far, guys? Questions, concerns?
No, I don't have any questions so far.
Okay, so Thursday, and so I'm giving you back time here, right? So again, this is kind of an agreement with your employer that I don't take more than 8 hours of your time a week. Notebook 3. Notebook, not sequel. Notebook 3. Yeah, Notebook 3. We're going to go over the Python format for if then else decision logic and how that works in Python. And then I'll turn you loose with some hands-on. Does anybody not have Anaconda installed?
Yes, sir.
You good, Dexter? And I know
Yes, sir.
Seth, you good?
Yeah, I've got it installed.
Okay, great. All right, guys. Like I said, giving you back some time. And that's good lab time. If there's anything I covered that you're like, I don't think that was quite right. This is a good time to go and Google it. And like I said, I'm not a mathematician. But through happenstance throughout my career, I've been forced into being an analyst and forced to learn this stuff, and I've got it in college a couple of times. So I'm not your PhD nerd that lives and breathes in this world daily. So let me know if I confuse you. Otherwise, everybody's caught up with assignments. I sure appreciate that. And I will see everybody Thursday morning at 8:30.
All right, see you then.
Okay, guys.
See you later.